Okay, moving on to lesson 12, we're in oxidation reactions, which of course I love because I kind of do that. Something to note here, you don't really need to know all of these mechanisms. Let's sort of know what they do rather than how they do it, because things can get kind of complicated, and truthfully there's a lot of things that we don't really know. But let's just leave it at that for now. You'll see the H2SO4, which we've talked about before. Get it? But I'm bummed. Okay. You can also have CR3 and H3O+. If you see a CR2O7, that would be basically the same thing. So know that those are kind of interchangeable. The problem with using chromium for anything is that it's kind of toxic and like kills people. But you know, you can't be too picky. So sometimes we kind of need to use that. If you use H2SO4 with a secondary alcohol, that's going to basically produce a ketone. So in contrast, using a primary alcohol is going to give you a carboxylic acid. I kind of look at this like all the hydrogens it could possibly remove and form more bonds to oxygen. It will use that, or use them all, if that makes sense. We use PCC on a primary alcohol to give you an aldehyde. So the difference here is that here you get sort of one stage of oxidation, and up here you get the maximum state. We do not get a carboxylic acid with PCC. Pyridinium chlorochromate, I believe is what that PCC stands for. So as a tertiary alcohol, neither of these can really do anything because they're not going to actually remove a carbon-carbon bond or break a carbon-carbon bond. And so there's no hydrogens to remove. It's not going to do anything in there. This is a really cool reaction. The Swerin oxidation uses NaOCl, which you may or may not recognize. That's actually bleach, household bleach. And if you recall from general chemistry, we have CH3COOH, which is vinegar. So bleach and vinegar together can take a primary alcohol and do the same thing as this nasty stuff up here can do, or somewhat similar to it. And it's also going to work on secondary alcohols. So here's the mechanism. First, the bleach, remember that's Na plus and OCl minus, along with the acid here, generates this type of structure in situ. I hope that you know what I mean by in situ. That means in the reaction beaker. So you're going to first make this stuff, and then you're going to start adding in your alcohol. And so this alcohol is going to come and grab that hydrogen, electrons go over, and you now just made a water molecule. And that water molecule will leave pretty easily, especially when attacked by a good nucleophile, right? Giving you this type of structure. Any basis in the reaction, even if it's solvent, can come and extract that hydrogen. The electron, sorry, I didn't write this the best way. So the electrons between this bond here, this carbon and the hydrogen, are the ones that come up to where that oxygen is, and the chlorine leaves. So that means we've formed a new double bond right there, and since the chlorine left, it's all done. It's really, really nice and easy. Okay, so just to let you know, since this wasn't mentioned last time, if you have an ether instead of an alcohol with this HX, that's going to work the same way as you had with the alcohols, and it's actually going to give you an alkyl chloride or alkyl halide, as well as an OH or another alcohol. So you can break apart epoxides into alkyl halides and alcohols, but you can't use HCl, because if you use HCl, it just doesn't behave very well. HBr or HI will work, and it depends on if you have a primary, it depends on your reaction conditions, again, whether or not you go SN1 or SN2. Okay. One of my favorite things to use is epoxides. Not only because they're very useful synthetically, you actually take a non-polar structure and make it polar. And so it's kind of oxy-cleaning your world, and if you want to consider it that way. So if you recall, an alkene in the presence of MCPBA or any peroxy acid, and there's a billion ways to do this, other than what we have here, but let's say that we're going with that, you end up with this epoxide. Well, this epoxide has a lot of ring strain in there, which means that nucleophiles can attack it too. Another way to make this epoxide is to first attack it with Cl2 and H2O. If you recall from last semester, that means that your water will end up on the most substituted position and your Cl will end up on the least. By having a strong base in here, they're also sterically in opposite directions, because you end up with the chloronium position here, if you recall that, right? You end up with a Cl bridge, and the OH has to attack from the opposite side. Okay, so if you have a strong base with this OH back here, this is sodium hydride. What that means is you've got an Na plus and H minus. So think about what that really is. An H minus means that a regular hydrogen would have one proton, one electron, right? So a H minus has one proton and two electrons. That is a pretty reactive little guy. And as a matter of fact, in order for that to even exist, you can't even expose it to air. You have to store it in oil. So we're talking about some nasty stuff here, right? That hydrogen can come and remove this hydrogen. It's a very strong base. That means that this oxygen having a negative charge would then react here and kick out that chlorine there, sorry. And remember, if we're talking about intermolecular reactions, it's much easier for you to reach down and touch your own toe than to go to the next house or building over and touch somebody else's toe. So intermolecular types of reactions are definitely easier to occur than intramolecular reactions, as long as something's right there, right? You've already got your very good nucleophile, you've got your good leaving group, and bam, bam, that just happens really, really fast. They're also in the right position to do that. Okay. We can attack epoxides either in acidic conditions or neutral in type of basic conditions. So let's stop with the acid first. If you have an acid of this sort, and really there's a lot of things that can work here, so not just halogens, but ethers or even water. This oxygen could come and grab that hydrogen, electrons move out. That means that we have a positive charge on this oxygen, so it is even more primed to be attacked by a nucleophile. This base is going to end up going to the most substituted position right there. Because if you want to think about it, as this guy is leaving, it's almost like a partial positive charge builds up on the carbon where it's leaving from. So that's going to be, or wants to be, on the most substituted carbon here. And that's why this guy goes to the most substituted carbon. It's much easier to understand that why than it is to understand or to think your way through this. Or, sorry, that made no sense, did it? It's much easier to think your way through this than to memorize it. That's what I was trying to say. Okay, so as this is leaving, we've got this guy coming in. This transition state's got a lot of charge buildup on it, and that's why the nucleophile, whatever that is, as it attacks, is going to go to the most substituted carbon. Okay, in contrast, if you were to have an epoxide attack with a base type of molecule, in this case we've got a negative charge on this base, and he comes in and he's going to attack the least substituted carbon for kind of the same reason as we saw up here. Because when this guy leaves, that oxygen has got a negative charge to it. And that negative charge needs to be stabilized by being on the most substituted carbon. So that means that this OCH3 will form a new bond between there and there, right here that you see right here, and this oxygen will have a negative charge to it. Once this oxygen has a negative charge to it, it can kind of grab any hydrogen from the solvent without a problem, and it does that. Usually use alcohol type of solvents here, but not necessarily that's the only thing that you can use. But once you have that hydrogen on there, then now this becomes a much more stable molecule. Okay, so the reason why you end up with sort of opposite products, in both cases, the charge of the transition state is, or formal intermediate, is on the most substituted carbon. Those are easy to get backwards if you don't think your way through that. You can also use epoxide synthetically to make sure that no rearrangement happens. So for example, if you were to have this alkene, an H2SO4 H2O, the first thing you would do is hydrogen would go to the most substituted carbon, leaving you a positive charge right here. But next door there's a tertiary position. So actually there's going to be a hydride shift. You're going to end up with a positive charge here, and then your water ends up going there, and that's going to be your product. Well, it's a problem if you actually wanted to put your OH right here. So an alternative would be to use MCPBA, give yourself an epoxide. Now we then have sodium hydride come in, and this, if it's acting as a base, it's acting as a base first, right? In the other case we saw something different. But this is acting as a base. It comes in here to the most substituted. That comes up. That leaves your oxygen as a negative charge. That oxygen then goes and grabs a hydrogen, and bam. So you can design your synthesis to give you really the product that you want, depending on what it is that you want, what you have. Okay, finally let's talk about diols. Diols mean that you have two alcohols. And we looked at last semester how we could use osmium for that. You can also use KMNO4. And there's advantages and disadvantages to each of those. But that's exactly what happens. Well, you can use epoxides to make trans diols, because the first thing that you would do is make an epoxide, and then when you hit this with OH minus, it's going to come in to the opposite direction of where that OH is, right? Then you can have any type of proton donor and end up with your product right there. You have to be careful here. You can end up with two products. Actually, you can end up with two products up here, depending on what's on the rest of the molecule, right? So you end up with trans in this case and cis in this case. Okay, thank you.